Today I would like to tell you something about machine learning and artificial intelligence for augmented visual inspection. And at first I will give you an overview. I will say some words about the role of machine learning with respect to the hype about artificial intelligence. And then I will discuss along some examples how methods of AI can be utilized in image processing and automated visual inspection. Machine learning is only a subset of AI. AI comprises much more topics, and I will show you later on that a lot of AI techniques can be used in augmented visual inspection beside of machine learning approaches. Artificial intelligence comprises, for example, perception, pattern recognition, cognition prediction, environment and context internalization, searching, planning. We will have two examples for planning in automated visual inspection, and behind that there are of course optimization techniques. Furthermore, reasoning, decision drawing under uncertainty, and so on. And last but not least, machine learning. And the recent success of AI is mainly due to the progress in machine learning. Why is it so? Why this renaissance of artificial neural networks? One thing is new architectures, for example, convolutional neural networks or long short-term memories, algorithmic innovations with respect to learning in such networks. You know all the many tricks you use to avoid overfitting if you learn a big, deep neural network with less examples than you have parameters in your network. The growth of computation power for all, especially with respect to GPUs, and the availability of huge amounts of data. This is not in all cases so that you have enough data, but the most intriguing examples where the ML technologies lead to extreme high performance image processing all use big data. The disruptive power of machine learning and image processing can be seen, for example, regarding the ImageNet large-scale visual recognition competition. It runs since 2010, and there are about 15 million images as training data, and we have there 1,000 categories to be classified. And if you look on, in 2012, there was a very interesting paper, ImageNet classification with deep neural networks from Grishevsky, and he solved this problem with a deep convolutional neural network. And as you can see here in the classification error of the competition over the years, in 2012, there is a significant reduction of classification error, and over the years, the performance of the CNNs reduced the error in a way that was not conceivable with traditional image processing methods. 2016, it was at 3%. Machine learning can be categorized into supervised learning, semi-supervised learning, unsupervised learning, and reinforcement learning. And these main topics can be divided into classification and regression, cluster analysis, manifold learning, graph structure, discovery, latent variable discovery and data completion and imputation. And in all these fields, the Fraunhofer IOSB conducts research with respect to certain applications, for example, classification in the case of bulk material sorting, or at the last write down image and video processing. We will have some examples for it later on. The first example I would like to show is the vehicle detection in aerial imagery. The problem is that vehicles in such images cover just a few hundred pixels. And if we want to classify and to distinguish on these vehicles, it is very difficult also for CNNs, because the standard, the state-of-the-art way to do this detection and classification are region proposal networks. These are networks that in the first stage they propose regions of interest where it is assumed that there are vehicles or candidates for vehicles, and in the next step, for each of these regions, a deep neural network tries to classify what's inside these regions of interest. And for each of these regions of interest, such a deep network will be established. The point is, this approach doesn't work very well if you have only images with a few hundred pixels, because the input images in this case are the regions of interest where the cars are inside, or the candidates for cars are inside. And so the CNNs cannot be really deep, and therefore a low performance arises. And a remedy for this problem is to include contextual information through upsampling of deeper layers. I'm not sure whether you can see my mouse here. Yeah, we sample up deeper layers inside the feature extraction, and then use regions also around the vehicles that we learn in order to produce better classification results. Additionally, we integrate semantic context through semantic labeling. And the trick is here that we learn additionally semantic labeling, but we don't use the result of this semantic labeling for the classification. But we learn simultaneously two tasks. We learn the detection and classification task on the one hand, and in parallel the semantic labeling. And we share the layers for the features. So in this way, the features are optimal on the one hand, or it's a compromise of optimality for the detection and classification task on the one hand, and on the same time for the semantic labeling. So indirectly, the information about the semantic labeling enters over the feature extraction into the network, and this leads to this proposed architecture leads to improved detection and localization performance compared with standard region proposal approaches. The performance is significantly improved, as you can see here on the lower right image, where you can see a comparison between the detection, the red rectangles, and the ground truth, the green rectangles, and the upper image is with the standard approach using region proposal this enhancement of contextual information. The second example is about detection of defects in textures here in textiles. At the left side, you see defectless textiles. On the right hand, you have you see possible defects. And as usual in such problems, it is easier to describe the defectless textiles than the huge universe of different defects that can arise. And usually you also have more data about the defectless case or the okay case than about the defect case. And the idea is here to train an autoencoder network that extracts in its bottleneck, here green, in the bottleneck, extracts a compressed representation of the texture. Then the decoder expands again to an image of the same size, and then you can subtract the image and the reconstruction. And if the representation through the network is good, the difference is small. That's the idea. And the trick is here that we learn these networks only with defectless textures. And so the network works later on as a filter that lets pass all the components of defectless texture. And then if we show to the network defective parts, for example, here, as you can see here as an input, then you have a difference in the reconstruction because the network doesn't know the defects. It does know only the okay texture and can reconstruct this texture. And then if we subtract both, we have a locally big error which we can use for defect detection in segmentation. The next example is about bulk material sorting. In this case, we apply it to grape sorting, here with respect to Schwarzriesling. Also here, we can characterize the good class or the okay class very well, and we have a lot of data for that. The not okay class, on the other hand, is polymorphic and huge. We also thought about one-shot learning, but in cases where the good class, the okay class itself has a very big intra-class variation, it usually is not possible to do it with a single shot. You need a lot of data to cover also the variation of the good case, if there is a variation. And this is done here with this approach. So we learn only with the good class, and this leads, like in the case of the texture example, instead of a multi-class classification, to the problem of a one-class classification. For the okay class, we have enough data, and one tries to enclose the data in the feature space as close as possible with a smooth boundary. Smooth is important to avoid overfitting in order to have a good generalization, also if you have not enough data. And the one-class classification is a very good approach for all cases. You have a lot of data, or you have mainly data for the good class, and beside deep learning approaches, several techniques for representation the okay class are available, like density and distance-based approaches, cluster analysis, hypersurface approaches, reconstruction-based approaches, as you have seen it in the texture examples. And we mainly work here with density-based approaches by learning hierarchical Gaussian mixtures. It is important to have here several techniques at our disposal, because in cases where you have more data, you can use, for example, deep learning technologies. And if you have only few data, then you better use parametrized models for the boundary, which can be easily learned also with a few data. In this example, vibrations of a wind turbine are measured during the operation of the wind turbine. As you can see here in the video, we learn using image processing methods and parametric models the dynamics of this wind turbine. And if we've learned it, we can drag it, and then we can point a laser on the rotor precisely on a certain point. And due to the Doppler effect, vibrations can be demodulated from the reflected laser light, and so we can measure the vibration spectra on each coin of the wind turbine during operation. And it really works very well. And if we then get back this information, the spectral information of the wind turbine, together with other features, we learn self-organizing coordinate maps. It's a kind of artificial neural networks in order to perform condition monitoring, to see that whether there is a trend, for example, or something has changed in the operation dramatically. So the next example is about the AI task planning, and it's about planning for deflectometric inspections. The problem in deflectometric inspections is that you have most of the times large and complex shaped objects, and you need a sequence of measurements for the full inspection of the surface. Think about a complete car, for example, or here a hood from a car. The measurement quality you achieve depends significantly on the sensor configuration, and the manual selection in the lab for sensor configurations is nearly impossible, because you have a combinatorial explosion, and it's very difficult to find good configurations to cover sparsely and with the required measurement uncertainty all the surface you want to inspect. And we did here a lot of work about the automatic generation of optimal measurement plans for automated inspection. We want to have a full inspection with minimal cost, and considering the required measurement uncertainty at each point of the surface. We solved the problem using a probabilistic approach, a Bayesian framework for representing the measurement uncertainty, and also the lack of knowledge consistently, with a probabilistic surface model, a measurement model, and uncertainty measure. And therefore, we can plan with this. And we use two different probability distributions. On one hand, Gaussian processes. On the other hand, a process containing discrete mirrors with probability distributions on the surface normal vectors. And with this, and together with some simulation we do for images which could be acquired in a certain setting, we perform an optimization of the coverage of the surface on the one hand, by respecting on the other hand the required measurement uncertainty which is required for the object under investigation. Yeah, and at the end we here get plans which are clearly superior compared with the plans that human being could achieve in the lab, also if he works many weeks for a complete inspection plan. The human performance is here outperformed far and away, and you see that plans here on the right side hand on the hood of a car based on a robot-based deflectometric inspection. It seems very strange, and I think it's difficult to find this optimal solution easily by experimenting in the lab, and we can show that this is a very extremely good solution for the problem with respect to covering on the one hand, and that you see also some overlappings, and these overlappings are necessary to respect the required uncertainty in these regions. So the last example I would like to show you is about laser triangulation and planning of 3D acquisition of complex objects. Laser triangulation is a very simple and established technique. A laser line is projected on the surface, and the camera looks from a different view on the laser line, and from the deformations of the laser line you can reconstruct this 3D shape. Simple to apply, but if you have very complex objects, for example, here a cylinder head, you have two problems. The one problem is that the surface is strongly reflecting, and the second problem is that the object has a very, very complex shape with a lot of cavities, and you want to acquire as much as possible from the surface, also from the cavities. And the question is how to place the laser, how to place the cameras, maybe in several acquisition rounds to get with minimal number of acquisitions a maximal coverage of the object with the required measurement uncertainty. And you can formulate it as an optimization problem, and then you can do planning within this optimization problem. And at the end, we did it here by a surface representation with Gaussian processes, which can also model easily and interoperably the measurement uncertainty. We put into this planning process the CAD model of the object, and together with some BRDF measurements, because in the cavities the reflectance of the surface is a problem, because in metal reflections you get double or triple reflections, which can lead to cross errors, and this should be avoided. So therefore we have also to use here the bidirectional reflectance distribution functions, which we measured in our labs. And we modeled the laser line precisely, physical precisely, and the sensors with we can do in our simulations. We can obtain from our simulation sensor realistic images of the laser line in on this complex object. And yeah, as you can see here, the right-hand side, this is a point cloud based on 10 optimized linear laser scans, and more than 95% of the surface is covered. And the optimization is done with respect to coverage on the one hand and measurement uncertainty on the other hand. And by no way by optimizing it manually in a lab, you are far away from this performance, which is achieved by this optimal planning. So that was my presentation. Thank you very much for your attention.